that these are not Lagrange degrees of freedom. These are not function evaluations, because as you know, Bernstein polynomials aren't, the values of the control points are not the values of the approximation. But conceptually, roughly speaking, you don't go too far wrong by thinking about that, and that refers to this identification. So I don't need to draw pictures of Bernstein polynomials for this audience. Why Bernstein Bezier? Well, elegant, efficient, stable algorithms. You've got lots of nice algorithms, these things, stochastic algorithms, and so on. These things are what are actually used for doing practical computations. These are what are more or less hardwired into the hardware so that I can do fast rendering, things like that, industry standard, and so on. So this is not news for you, but this would be a big news for finite element audience. This is what is used in industry for dealing with high order polynomials and visualization. I mean, the situation is quite often you'll see someone giving a high order finite element talk and they'll solve a problem in 3D using degree 10 elements, and then they'll kind of have a rendering of this thing. And if they're very advanced, they might even have an animation. And what you find is as they try and rotate the mesh around, it does this. Like, no, mine doesn't even rotate at all, but I mean, it goes very slowly, and you wonder, how can this be? When my children are playing with games that have got many more degrees of freedom of this, and the thing can move around as we like, and it's essentially because of this technology going on behind. So why are the finite element people not using it? So that's why Bernstein Bezier. We want to try and take advantage of these algorithms that give very stable evaluations and so on, and yet at the same time can be translated into fast hardware solutions. So why has nobody else, or why have people not decided to just use Bernstein polynomials as the bases before? Well, of course, people have,